Welcome. Now we'll consider the idea of equivalence relationship on a set, and we might do an introduction to cardinality. So, a different way of associating to a set A another set is through an equivalence relationship on the set A, which is a relation between some pairs of elements A1 and A2, which is denoted by A1 is equivalent to A2. And any equivalence relationship must obey the following three properties, namely reflexivity, symmetry, and transitivity. These are the same that equality obeys, so it's easy to consider them in the case of equality first. So for natural numbers, clearly a number is equal to itself, and if a number is equal to another number, then that other number is equal to the original. And finally, if you have three numbers, and A is equal to B and B is equal to C, then A is equal to C. This is exactly the same case as you have for equivalence relationships, except instead of equality, you have equivalent, or the equivalence relationship of interest, and you can consider any elements in your set A. If this equivalence relationship is in fact an equivalence relation on a set A, then to any A in A, there can be associated to that element A the set of all other elements X in A that are equivalent to A. Namely, A sub A is going to be the set of all X in A such that X is equivalent to A, and you can clearly see that's a subset of A, but they may be equal. In particular, by reflexivity, we have that A is for sure an element of the subset A sub A. This set A sub A is called the equivalence class of A with respect to the equivalence relation. Similarly, to any element B in A, that can be associated with the set A sub B of all Y in A that are equivalent to B. However, if you have a set C that is in the intersection of two equivalence classes, then it must be the case that those equivalence classes are actually equal. This is because if C is in the intersection, then it is the case that C is equivalent to A and C is equivalent to B. So by symmetry and transitivity, A is equivalent to B and B is equivalent to A. So any element in A sub B is equivalent to B and therefore equivalent to A, and therefore is an element of A of the equivalence class of A. And so that proves that the equivalence class of B is a subset of the equivalence class of A. And likewise, you can prove the reverse and see that the equivalence class of B is a subset of the equivalence class of A. The equivalence class, yes, that's correct. You'll note that here they do that in slightly different order, but it does not matter. But in fact, you see that they're equal. Thus, if you have sets of disjoint equivalence classes, namely those that do not share any elements, you get a partition of the set. Or if you consider the set consisting of only these various equivalence classes, you call this the quotient of the set A under the equivalence relation that you defined here. This is denoted by A is a quotiented with respect to equivalence class. This is a construction that arises very frequently. For instance, for any mapping F from A to B between two sets A and B, there can be associated an equivalence relation on the set A by setting two elements equal with respect to equivalence relation F, namely this symbol, for any 2 points A1 and A2, whenever it is the case that their images are the same. It's quite clear this is indeed an equivalence relation, and the quotient, A quotiented by the equivalence class of F, can be associated with the image F of A of B, since that will have unique images and such. The notion of equivalence also is used in a slightly different way, as a relation among sets, rather than as a relation between the elements of a particular set. For instance, the equality of two sets clearly satisfies the equivalence class definition, but it is not phrased as an equivalence relation between elements of a set, rather as an equivalence relation among various sets. This is done in order to avoid the idea of a set of all sets. As another example, two sets are said to be equivalent if there's a bijective mapping F from A to B, and one way of writing this is A is bijective of B equivalent to B. Lots of ways of writing this. Some people will even say isomorphic if there's further structure that's preserved between these two sets. Using this symbol, we also have another equivalence class, such that you can consider the idea of equivalent sets. And equivalent sets intuitively are those with the same number of elements, in the phrase of Gunning, whatever that may mean. One possibility for defining the number of elements in a set is by using the equivalence relationship itself as a proxy for it. That is what we will define to be the cardinality of a set A. This is merely the equivalence class of that set, namely the set of all x, such that x is a set for which x is equivalent to A. With this definition, we say the cardinality of A is equal to cardinality of B, just meaning that A and B are determining the same equivalence class, or namely that they are equivalent to one another. So there's a bijective mapping between them. For instance, if you have two sets of cardinality 2, then they're clearly equivalent to one another. All right, we'll continue with cardinality next time. Thank you.